Hi, physics. Mr. Janowski here, and today we're going to cover some of the most important slides that you're going to get to all year. And unfortunately, you're watching me give them to you recorded from my living room and not in person. So that's a shame, but it is what it is. So without further ado, let's get started. Let me minimize myself a little bit here. All right. Hopefully, you still get the sense that I'm up there. For some reason, the camera's lengthening my head. Uh, my head is not this tall and narrow; it's much more round and less handsome. Anyhow, first question. When does mechanical equilibrium occur? Use a sigma in your answer. So, thinking back to chapters 2 and 3, mechanical equilibrium occurs when sigma f equals 0. When the sum of the forces on the object is 0, you're in what's called mechanical equilibrium. So, question 2, describe the motion of an object that is at rest and in mechanical equilibrium. Well, if it's at rest and there's no net force, it's just going to stay at rest. Question 3. Describe the motion of an object that is moving and in mechanical equilibrium. Well, if it's already moving and there's no net force, it's going to move straight line, constant speed. That's a phrase that physics teachers say thousands of times in their career. Straight line, constant speed. So those first three questions deal with things we dealt with in chapters 2 and 3. Inertia, Newton's first law is the law of inertia. It's really Galileo's idea. The next two questions deal with, well, what happens when sigma f does not equal 0, when there is a net force on the object. So what do you think is going to happen to an object that is at rest but not in mechanical equilibrium? So sigma f does not equal 0. Well, that thing's going to start to move. It's going to start to accelerate. And question 5, what do you think would happen to an object that is already moving, but it is not in mechanical equilibrium? So sigma f is not 0. Well, it's not going to go straight line constant speed. Either it's going to change its direction or it's going to change its speed, or it might change both. So these chapters get a little bit harder. So your next test will eventually be chapter 6 and 7. Chapter 6 is Newton's second law. Chapter 7 is Newton's third law. And we will spend the vast majority of the time on chapter 6, Newton's second law. Chapter 7 will go by fairly quickly. So, what is a force? Remember that a force is a push or a pull. Every force pushes or pulls. And remember also that forces change an object's state of motion. Now, Galileo thought that you need a force, a violent force, imposed upon an object to keep it in motion. And then Galileo and Newton came along and they realized that no, you don't need forces to keep objects in motion. If there's no net force and the object's already moving, it will stay in motion indefinitely. Forces change motion, but they're not required to keep things moving. They change motion. So I'm just recycling some old slides here. The symbol for force is almost always going to be a capital letter F, sometimes with a subscript. So you have F sub g, or F sub little g. This is the force due to gravity. In everyday English, we just call this weight. You have F sub capital N. This is the normal force. And if you have Alice, Billy, and Charlie, and they're all applying forces to a thing, then you would call those forces F sub A, F sub B, and F sub C. Notice, by the way, that I'm saying F sub A, not F of A. That would be F, which is a function of A. I'm saying F sub, S-U-B-A. Anyhow, the most common unit for force is the Newton, written as a capital letter N. Pounds are also units for force, but in science class, we're going to use newtons for force and not pounds. So the definitions for these things here. Weight F sub g, this is the force due to gravity between the mass and usually the Earth. Unless otherwise stated, assume that the thing is on the Earth, not on some other planet where it would have a different weight, not on the moon, anything like that. Unless otherwise stated, you can just assume that we're on the Earth. Normal force. This is why we don't use your book, is your book calls it support force, and no physics teacher ever, anywhere, has ever called it support force. It's always normal force. This is just what we call it. It's not normal in the sense of being typical or regular. It's normal in the sense of being perpendicular. And whenever two things touch each other, there's always a normal force between them. So as my hands come together, one hand is putting a normal force, going that way. The other hand is putting a normal force going that way. Normal means perpendicular in this case. So right now I'm sitting in a chair. My weight, the force of the earth acting on me with gravity, is pulling me down towards the center of the earth. The reason I'm not accelerating downwards is my chair is exerting a normal force up on me. Then there's also forces of friction, F sub k for kinetic friction and F sub s for static friction. The resistance of objects across each other. More on those when we get to them. And you also have tension. So F sub t for tension, or maybe you would just use capital T for tension. The force due to a string, rope, chain, or the like. So, for example, right now, the elevator is hanging in the elevator shaft. Um, there's a cable pulling up on the elevator car, and there's tension in that cable, and that's what's providing the force, is the tension in the cable. So that's one case where you might use T instead of F to symbolize that force, the force of tension. Remember also that forces are vectors. So everything we deal with this year will either be a scalar, meaning it has only a magnitude, just a size, or it will be a vector, meaning it has a magnitude and a direction. So forces are vectors because they have both magnitude and direction. You can have a 100 Newton force directed up, down, left, right, to the east, north, at a 30-degree angle. Oh, I should do it for the camera. At a 30-degree angle above the horizontal. Um, yeah, forces have direction. That makes them vectors. So here is a very famous person. This is Lionel Messi, who used to play for Barcelona, as he's pictured here. His nickname is La Pulga Atomica. So that means the atomic flea, FLEA, flea. He has this nickname because he's a fairly small person. He's actually a little bit smaller than me. He's listed at like 5'8", but in reality, he's probably shorter than that. He's probably more like 5'6" or something, which is not terribly small, uh, for an adult man. But for one of the most famous athletes in the world, and Leo Messi certainly is, that is a little bit short. It's odd that they would be, that small and still a world famous athlete. Anyhow, doesn't matter. Point is, he's the atomic flea. Um, so Leo's going to kick the football, which is, in America we'd call this a soccer ball. Most of the world would call this a football, and a bowling ball with the same amount of force, and yet the bowling ball's motion is going to change less. So you know that intuitively. Why does the bowling ball not move as much if Leo puts the same amount of force on it? And the reason is the bowling ball has more mass, and mass is inertia, and inertia is reluctance to changes in motion. The bowling ball doesn't, both of these things are at rest, sitting there on the ground. When you put a net force on one of them, the one with more mass, if you put a net force on both of them, the one with more mass is less willing to move. It's more reluctant to move. So this is the part where I go into a whole big spiel, and I'm sad that I won't be able to do this in person this year. In that, for some of you, this is the only physics class you will ever take in your entire life, which is kind of sad. Some of you will take more physics. Some of you will take physics 2 with me next year. Some of you will take physics in college. But for some of you, this is the only physics class you'll ever have in your life. And, that puts an important responsibility on me. So imagine yourself 20 or 30 years from now, sitting around by your fireside, and Junior, some smaller version of yourself, comes up to you and asks, Mommy or Daddy, I need help with my physics homework. Do you know anything about physics? And you might say to this person, I'm sorry, I took physics in high school, but I don't remember any of it. But then you will stop yourself and you will say, that's not completely true. I remember one thing. The one thing you absolutely must remember from physics this year is the thing that is on the next slide. This is the absolute most important thing. And that thing is that F equals ma. Force equals mass times acceleration. This is Newton's second law of motion. This is so simple. One thing equals one thing times another thing. Force equals mass times acceleration. So very simple and elegant, and yet this explains so much. So I want to go on and on about this, but in the interest of keeping this video short, let me not do that. Let me just point out again, this is pretty much the only thing that's ever really happening in the universe. Forces are accelerating masses. That's basically all that ever happens. A simple idea, but if you know how to apply it and apply it and apply it, you see that this is really the only thing that's ever really going on. So same situation, only this time we have some numbers and we have some math, and having math makes this a very powerful idea. So if Leo Messi kicks the football and the bowling ball with the same force, and the bowling ball has 16 times the mass of the football, how will their accelerations compare? Well, we knew that the football was going to accelerate more and the bowling ball was going to accelerate less. But now that we know Newton's second law and we know how these things relate to each other, um, we can come up with the actual number. So if F equals ma, well, that means A is equal to F over m. So if you put the same amount of force in both of these things, but the football has 1/16th the mass of the bowling ball, the football will end up having 16 times the acceleration of the bowling ball. Um, that's it. That's Newton's second law. F equals ma. If you know the force and the mass, you can figure out the acceleration. If you know the mass and the acceleration, you can figure out the force. If you know any two of the three, you can figure out the third thing. So this is the image I want you to associate with Newton's second law. F equals ma. So for example, let me drag my picture out of the way a little bit. It's a bit in the way. Here's Newton's second law, how I want you to remember it. And here are two other versions of it, just solved for A and solved for M. So in the first one, what force is required to accelerate a 50 kilogram mass at 2.2 meters per second squared? Well, if we were going to do step what we'd be looking for is force. What force? We want the force in units of newtons. Well, F equals ma. So plug in for M, plug in for A, and you end up with 110 newtons. Second question, what would be the acceleration of an 80 kilogram mass experiencing a force of 120 newtons? Okay, well, this time we're solving for A, so we would use this middle version here. A is equal to F over M. Plug in for F and M. 120 newtons divided by 80 kilograms, you end up with 1.5 meters per second squared. And finally, an object is accelerated at 9.8 meters per second squared by 735 Newton force. Perhaps someone dropped it. What is the object's mass? Well, step we're looking for mass in units of kilograms. So we would use this version, m equals F over A. Plug in for F, plug in for A. 735 divided by 9.8, you end up with 75 kilograms is the mass of the thing. So in your first homework, this is really all you need to know is this formula. Figure out what you're looking for, figure out how to solve for it. The first several problems are really this easy. After that, they get a little bit harder. Give it your best. And hopefully I'll be back in person very quickly to show you how to do these problems.